Hi guys, in this lecture we'll be starting off with the flipping of um, cyclohexane ring, which is in chair form. So let's start. So flipping. Okay. So let's suppose we have this cyclohexane ring. So what actually happens is this cyclohexane ring actually undergoes flipping at room temperature, and it converts into various forms like boat, half boat, um, twisted boat, and structures like that. So we'll see the first structure as um, something like this. Then it actually gets converted into beg- something like this. It can also get converted into what is called half chair. It can also get converted into a boat. This is called half chair. This is called a boat, and it can also get converted into something like this. Okay. uh, so this was the first example, and in the second example what can happen in a flipping is that suppose we have CS3 at the axial position at this carbon atom, and suppose we flip it. So what can happen is, on flipping, this CS3 can come into equatorial position. Okay. So on flipping cyclohexane, the equatorial bonds will convert themselves into axial, and axial will convert themselves into equatorial. Okay. So just remember this fact, and you can draw any of the flipped structure when you are asked to draw. So suppose you have ET and you have CS3 here, so you decide to flip it. Hands on flipping, what will happen is, the equatorial bond of ET will convert into axial bond, and the axial bond of CS3 will convert into equatorial bond. Okay, so this would be the structure on flipping. Okay, so in flipping, all axial bonds convert into equatorial and all equatorial converts into axial. So let me write this again. In flipping, all axial bonds will convert into equatorial, and all equatorial will convert into axial bonds. Okay, so let us look at the graph which we can see at energy level. So this is the energy level. So uh, this was our chair formed cyclohexane ring. So what will happen is this can take the heat, undergo some transition, and can form or convert itself into half chair, something like this. And this half chair can then convert itself into what is known as twisted boat. So its structure would be something like this. Okay, so these bonds actually are coming towards your side, and the rest going these two bonds are coming towards your side, and these two bonds going away from your side. Okay, so this is known as twisted boat. To be more clear, let me redraw it with a bigger size. So we have something like this. Okay, 1 2 3 4 5 6. So these bonds are actually twisted. So let me make the dash so that you can understand that this bond is going inside the plane, and this is also inside the plane only, going away from your face. And actually this bond is actually coming towards your face, hence in dark. Okay, so I hope you can understand this figure. So this is called twisted boat. Okay, so now this can also go into some conversion and form itself into a boat. Okay, this is half chair, this is boat. Okay, now this boat will again can convert into what is known as twisted chair, and this twisted chair can get more energy and convert itself into again half chair, and we can again get cyclohexane or full chair. Okay, so this is the graph. Okay, so relative stability order is relative stability order is chair is more stable than twisted boat, and twisted boat is more stable than boat, which is more stable than half chair, as can be seen in the energy diagram above. Okay, so I hope you remember this. This is important relative stability order in case of cyclohexanes. So boat is actually unstable than chair because of flagpole hydrogen depolations. So if you see the structure of boat, it is something like this. So what happens here is we have two hydrogen atoms on the extreme carbon atoms. So the repulsion between these two hydrogen atoms causes this boat to lose stability over chair, hence chair is more stable than boat. Okay, but in case for example, if we have some compound like here OH and here OH, so boat structure in this case would be more stable than the chair. Why? Can you guess any reason? Boat is more stable in this case than chair. And why is this the reason? Why is this the case? Because when you draw the board structure for this, you see that OH attached here and OH attached here. So this OH actually undergoes into intramolecular hydrogen bonding. So due to the formation of hydrogen bonding intramolecularly, this compound or this conformer becomes more stable than chair. Okay, so in the next lecture we'll be talking about melting point, and then we'll be quickly moving on to optical isomerism. So till then, good luck and goodbye.